Okay, so how many of you have some type of experience with Pythagorean theorem? Because this is something I've seen has more and more migrated to like the middle school level.
I remember doing it.
Well, there was this guy named Pythagoras who figured out that if you have a right triangle, how many sides does the triangle have? And if it's a right triangle, what do we know about?
90 degrees.
That we have exactly one angle that's 90 degrees. Well, if you take the two sides that meet at the 90 degree, which would mean that that angle would be the included angle at 90 degrees. So the two sides that flank that, we're going to call those the legs. And then the side that is opposite of the 90 degrees, we're going to call that the hypotenuse. So he figured out that if you get the sum of the squares of the legs, sum, which means plus, squares, which means second power, of the legs, A and B, that would be equal to, in a right triangle, only in a right triangle, that would be equal to the square of the hypotenuse. Square of the hypotenuse. So you can use this to find a missing side, but in order to find a missing side, you have to be given the other two. In any equation, going back to the good old days of Algebra 1, if you want to find a numerical value for a variable, how many variables do there have to be? If you want to be able, you can always solve for any variable, but if you want at the end to be able to get like x equals and then a number, if you want to get a number as an answer, how many variables can you have? Just one. If you look at Pythagorean theorem, how many variables are there? How many unknowns? How many letters are there? 3. So if you want to figure out how big, like what's the number for one of those 3, they have to give you the other 2. The legs are interchangeable. There's no rule that says that A has to be the shorter leg and B must be the longer leg. No, it doesn't matter. A and B are interchangeable. But C has to be the hypotenuse. Some people know the hypotenuse as being the longest side. Yes, that is correct. On a right triangle, the right angle has to be the biggest angle. Therefore, the side that is across from it, that is opposite it, must be the biggest side as well. Biggest mistake that happens with Pythagorean theorem is that people don't substitute where they're supposed to substitute. They plug in the hypotenuse where one of the legs go. They plug in the one of the legs where the hypotenuse goes. We're going to have a little mini unit now that's on all right triangles, and I was looking at, I believe, I want to make sure I'm not confusing this with Algebra 1, but I'm pretty sure I'm not. For the rest of the semester, mostly what you have are quizzes. But the only test that remains is a test on right triangles. That test will include Pythagorean theorem, and then what we'll start learning next week, which are special right triangles and your favorite trigonometry, which sounds more complicated than it really is. Trig of what? Trig of who? Just in case it ever comes up, and those of you that are extra studious, there is something known as Pythagorean triples. Think of Pythagorean triples as being like little cookie cutter numbers that we have already tested and work with Pythagorean theorem. Like the first Pythagorean triple is a 3, 4, 5. If you have a triangle where the legs are 3 and 4 units long, it could be inches, centimeters, feet, whatever it is, but if you have legs that are 3 and 4 units long, and you have a hypotenuse, the third side is 5, that has to be a right triangle. These numbers work in Pythagorean theorem. What is 3 squared? Please don't say 6. No. It is 9. What is 4 squared? 16. What is 9 plus 16? 25. And what is the square root of 25? It is 5. Any multiples of these also work. So like if I were to get all these and multiply them by 2, that would be 6, 8, and 10. Those 3 sides would also, if you get like sticks that are 6 inches long, 8 inches long, and 10 inches long, if you connect them at the tips, you're gonna have to make a right triangle. If you multiply all of them by 3, like any multiples of these triples will always work. So the other in order to be a Pythagorean triple, No decimals, no fractions. They have to be whole numbers. So the other main ones are a 5, 12, 13 right triangle, an 8, 15, 17, and a 7, 24, 25. If you were ever asked to prove that a right triangle was right, and you didn't feel like using the theorem, if it happened to have these sides, you can state the fact that you've memorized your Pythagorean triples. Do you have to memorize Pythagorean triples? No, but if not, then you'd have to use the full theorem. These are just some. These are not every single right triangle that exists. It's just these are just some that are easy to remember because they have no fractions and no decimals. If we see these along the way, then I'll point them out to you. So now we can already get into the examples. Find x. How many triangles do you see here? Three. It appears that there's two right triangles, and then there's a bigger one. And what word can I use to describe the bigger one? It is isosceles, sure, because two of the legs are congruent. Yeah. And if you really want to impress me, there's a special segment that is drawn on the inside of this isosceles triangle that goes from the vertex angle down to the base, and it meets it at 90 degrees. Which special segment starts at an angle and goes to the opposite side and meets at 90 degrees? There's 4 special segments. We learned about them earlier this year. You also saw them on the construction. The Pied Piper? The Pied Piper? It is an altitude. Thank you very much. By definition, it's an altitude. But because that altitude is coming out of the vertex angle of an isosceles triangle, it also acts as a perpendicular bisector, as a median, and as an angle bisector. It's all of the above. So this is going to help us because it not only is meeting the other side at 90 degrees, it's also bisecting it. If the entire bottom, the entire base is 14 units, and it's cutting it in half, what are each of the smaller triangle lengths down there? 7, yeah. 7. Okay. So now I want to take your attention away from the isosceles triangle, and let's focus on either one of the right triangles. It doesn't matter which one. Let's just focus on this one. For x, and that's what x is part of. Now this is a right triangle. What side of the right triangle are we looking for? We just gave the sides names. We're looking for a leg. Did you say an angle? So you're just like shouting out words that you've learned and stuff. You just want to. Oh, the angle is 90 degrees. The x is the side leg. So Pythagorean theorem says a squared. This is the only time I'm going to write this again. It's already on your notes. Where a and b are the legs. If I'm looking for a leg, I can put this x on either one. It doesn't matter. I'll normally write it on the first one, but it doesn't matter. Okay, so I'll write x squared plus, what's the other leg? Huh? No, it's not going to be, because I know you better know what b is. Like once you have one variable, there better not be any more variables, and now you're not going to be able to solve. It's 7, yeah, so we just found plus 7 squared equals 8 squared. So x squared plus 49 is equal to 64. X squared, minus 49. X squared is equal to 15. And then I told you that a very common mistake with Pythagorean theorem involves substitution. I'd say that this is even worse. What do we do with that last square? There's 3 mistakes that are made. One is substitution. The other one would be here in the middle. People don't know whether to add or subtract. And then this is the last one as well. How do you get rid of a square? You should take a square root, but it's not just as easy as that. Because Yeah, it's like if I say instead of 15, that would have been 16. Yeah, okay, no big deal. Nobody makes a mistake there. What's the square root of 16? 4. You might have learned in algebra 1 that it's actually plus or minus 4, but since we're looking for a length, it can't be negative. You can have a negative length, so it would have just been 4. But 15 is not a perfect square. So it depends on what the instructions tell you to do. One type of instruction would be very calculator friendly, and it would say, hey, Scotty, put square root of 15 into your calculator since you're our local calculator guy. And you should be getting like 3.8 something maybe. 3.87. But it fills up the screen, right? And if you had a bigger screen, it would fill that up too. And if you had the biggest screen on earth, it would fill that up too. Because that's an irrational number. It's going to go on forever. So more than likely, if that were the case and they wanted you to use your calculator, what would the instructions tell you to do? No, fractions not going to work. Huh? To round. It would ask you to round. It would say round to the nearest tenth, round to the nearest hundredth, whatever it may be. I'm going to bypass those set of instructions because I'm going to assume that if that time were to come, you would know how to put it in the calculator. What I want to focus on are the other types, which actually ask for an exact solution. It's not rounding. Exact would mean you have to simplify that radical, the tree. If I put 15 into a factor tree, can I bring out any prime factors? Are there any pairs? No, I cannot. So what's going to happen? It will just stay the same. X is equal to the square root of 15. Why didn't you just say that in the first place? Any questions there? See if I can do like one or two more before we. What are we looking for here? Yeah, the hypotenuse. So, does it matter which leg I write first between the 20 and the 28? No. It doesn't. So I'm going to write 20 squared plus 28 squared is equal to x squared. 20 squared is 1200. 28 squared is it like 576 maybe? What's 28 squared? 5 what? 784. So 1184 is equal to x squared. Now, I don't know off the top of my head if 1184 is a perfect square. So regardless of what the instructions say, I'm going to put that into my calculator. I'm going to take the square root of both sides, and I'm going to cross my fingers. It gave me a decimal? Okay, so that means if the directions say to round, then go ahead and just round. But if not, we would simplify this. That's 2, 592. Somebody check my math on that. 1182 divided by 1184 divided by 2. Divide that by 2, that's going to be 296. Divide by 2 again. That's 148. Divide by 2 again. 74. Divide by 2 again because it's still even. And that's prime. So I can bring out 2 2's. 2 times 2 is? 2 times 2 is 4, as the cool kids say. And then 2 times 37 is what is this? I don't know. You guys should know how to do a factor tree from algebra 1. Have we done that in here this year? Alright, we'll stop it there and then we'll continue tomorrow. Yes, ma'am. Okay, but